Okay, good morning, everybody. Let's get started. Good morning, Fort Walton. Okay, so before we start today, I want to go back to the example that we've done in the previous class, and that was the high-pass filter. So if you remember, if we have a transfer function that was z over z plus 0.5, that was a high-pass filter. And if we look at this filter, if I look at the frequency response of the filter, when omega is equal to 0, what was the gain? 2 over 3. This is the frequency response. When the frequency is pi, the gain is 2. Make sense? So then we went and we said, oh, okay, let's demonstrate that and show that indeed if I put a signal that is very low frequency, which is this signal, which is omega equal to 0, I should get it will get attenuated. And if I put a high frequency, which was a pi, it should get amplified. Remember that? Mm-hmm. So indeed, I mean, I went back, instead of calculating it by hand, I let MATLAB plot it. And you cannot see anything, of course, but if you trust me, or we can amplify it, if you look at what happened to the signal when it has a 0 frequency, what was the steady state amplitude of it? Can you see it?
It decreased.
What is it?
0.7-ish.
Less than 0.7. How about 0.66? Okay. And then if I look at the steady state value for the signal that has an omega that is equal to a pi, what is the steady state value for it? 2. A 2. Now, where is this 0.66 and coming from and the 2 coming from? If I go back to the frequency response, this tells me the gain if the frequency is 0 is 2 over 3, which is 0.66. The gain if the frequency is pi is 2. Make sense? So I just wanted to point that out. Okay. Okay, so far we looked at the different representations of the system. So hopefully now everybody is familiar with the impulse response, difference equation, frequency response, transfer function, and you can go back and forth between any of them. Now I want to add to this graph that we have here that summarizes everything that we learned. So just a few notes to add. So the system is stable if and only if h of n is stable, and that is the same as saying the region of convergence of h of z contains the unit circle. And in this case, if it contains the unit circle, then the discrete time Fourier transform will exist. So this is the first observation. The second observation, if the system is causal and stable, then all the poles are inside the unit circle. And if the system is anti-causal and stable, then all poles are outside the unit circle. Make sense?
That's uncausal and stable.
Anti-causal and stable.
Anti-causal and stable.
Yeah. So again, if the system is causal, if this is the unit circle, then all the poles have to be inside the unit circle. And therefore, if I take the largest pole that exists, it has to be such that it is within the unit circle. So this will be my region of convergence if the system is causal and stable. And if the system is anti-causal, and stable, then all the poles have to be outside the unit circle. So therefore, in this case, my region of convergence is going to be something like this. This is my region of convergence. Together? So remember, region of convergence, if the system is causal, is going to be to the outside. It has to include the unit circle. So the only way it's going to include the unit circle if it looks something like this. If the system is anti-causal, then the region of convergence is going to be to the inside. And the only way it can be to the inside and include the unit circle if it looks something like this. So this will be this somehow, somewhere here, this is the smallest pole of the system. Does that make sense? Everybody? Okay. Okay, so what we're going to be doing today is we're going to be looking at the stability Go ahead, quick. Okay. So what we're going to be doing today is we're going to be looking at the stability, and we're going to introduce a tool that will help us determine the stability of a system. And after we finish the stability, we're going to start the next part of our course, which is filter design. So starting with stability, we said a system is stable, and of course with stability we means bounded input, bounded output stability, if and only if h of n is stable. And h of n is stable, it means h of n. What is the condition on h of n for the h of n to be stable? Does anybody remember? More accurately?
Some of the absolute values are finite.
Excellent. The summation of h of n, all the terms of h of n from 0 to infinity, has to be finite. So that is the case if the region of convergence of h of z includes the unit circle. Okay. So therefore, if h of n is stable, then the summation from n equal negative infinity to infinity, absolute value of h of n has to be finite, less than infinity. And again, this is the same as saying the region of convergence of h of z must include the unit circle. If the system is causal, then bounded input, bounded output stability if all the poles of H of Z lie within the unit circle. Does that make sense, everybody? Can anybody explain to me why, if the system is causal, then the bounded input, bounded out stability means all the poles of H of Z must lie within the unit circle?
If they're not, then the denominator goes to infinity, or zero?
Yes. Another explanation. Okay, so we have this graph that shows all the responses based on the pole location. And hopefully, like, it should be semi-familiar. If I have H of Z over Z plus 0.5, this is going to equal to, H of Z over Z minus 0.5. The pole is at 0.5. H of n is going to be 0.5 to n, which is going to be starting at a value and then just decaying. Make sense? So is this stable? If I look at this,
Yeah.
stable. Because if I add all these terms, they're going to add up to a finite value. Make sense? Now if I start moving this pole to the right, and I have the pole at this location here. If my pole is at this location, and let's say this location is 0.9, what is the response going to look like? It's going to look similar, except 0.5 is going to be 0.9. So it's going to start at 1, then 0.9, 0.9 squared, and it's going to keep decaying. Make sense?
Yeah.
Now if I keep moving this pole, and now the pole all of a sudden is on the unit circle, what is H of n going to look like? It's going to be a unit step. This is Z over Z minus 1. It's a unit step. Is this system stable?
No.
It's not stable. Even though it looks finite, if I add all the terms, they're going to add up to infinity. Make sense? So it's not stable. So it looks like, makes sense. If the pole within the unit circle, it means the term that I'm going to, when I calculate x of n, is going to be some value a to the power of n, where a is the pole location. If a is less than 1, then when n goes to infinity, it's going to go to a 0. If a is 1 or greater, it's not going to decay. It's going to grow and it's going to get larger and larger, which is what we see here. If I have pole outside the unit circle, what is the x of n or h of n going to look like? It's going to be a growing exponential signal, and therefore it's unstable. So the only way the system is going to be stable if all the poles are within the unit circle. Make sense? But if the system is causal and all the poles are within the unit circle, the region of convergence is going to be outside the largest pole. But if it is outside the largest pole and all the poles are within the unit circle, it's going to include the unit circle. Make sense? Okay. So therefore, we want to look at a tool that will help us determine the stability. How can we test H of Z equal to B of Z divided by A of Z for stability? What is the obvious option?
See if the zeros of A of Z are inside.
Yes, see if the poles of the system, the zeros of A Z are the poles. We can factor A of Z and find poles and see if they are within the unit circle. Does that make sense? Is this an easy option? When I do like this, it means no. Is this an easy option? No, this is difficult. I mean, you guys were complaining about the third column a minute ago. So this is difficult. Of course, assuming you don't have access to MATLAB or a calculator. So therefore, when I create a table test for stability, and this is what we're going to be doing. We're going to be creating or introducing a tool that will help us determine the stability of h of z. And to do that, we're going to define a Shor polynomial. And a Shor polynomial is a polynomial that does not have any roots outside or on the unit circle. Does not have roots outside or on unit circle. So therefore, a Shor polynomial is a polynomial that does not have any roots outside or on the unit circle. So therefore, if we're talking about causal system, which is what we are talking about, for a causal system, if a of z is a Shor polynomial, then the system is stable. Does that make sense? The Shor polynomial is the polynomial that does not have roots on the unit circle or inside. If a of z is a Shor polynomial, then it means the system is stable. Okay, so how do we test to know whether the polynomial is a Shor polynomial or not? So if we are given a polynomial a of z equal to an z to n plus an minus 1 z to n minus 1 all the way to az plus a0, we can create another polynomial that we're going to call a1 of z that is going to equal to 1 over z an a of z minus a0 z to the n a of 1 over z, which is going to equal to cn minus 1 z to n minus 1 c1 z plus c0. Now a of z is going to be Shor if and only if a0 is less than or equal to an. So this is the first condition. And the second, a1 of z is Shor polynomial. And this process is recursive. What does all this mean? So we're trying to determine whether a of z is a Shor or not. And what it says, generate a1 of z. A of z is Shor if a0 is less than an, and then also a1 is a Shor. So you have to do the same thing you have to test for a1 of z, and keep going, generating a2 of z, a3 of z, etc. So we're going to introduce a tool that will help us do this calculation easily to determine if the polynomial is assured or not.
We need a tool for the tool for the tool.
A tool for it. Well, the tool is what we're going to introduce. All this is the theory behind the tool. The tool is going to help us with the calculation.
I didn't finish in K, but that's absolute value A not less than absolute value N not greater.
Yeah, the absolute value of A0 is less than the absolute value of AN. A0 must be less than AN. And the same thing. A1 of Z is sure, and therefore C0 is less than Cn minus 1. Okay. So we're going to look at Jerry's table test for stability. And to use this table, we're going to write the coefficients of the polynomial in descending order. So the first line will have the A of Z and descending powers of Z. Now on line 2, we're going to reverse the order of the coefficients. So therefore, we're going to have something that looks like this. an minus 1, an minus 1, an minus 2, all the way to a2, a1, a0. This is A of Z. And then we're going to have a0, a1, a2, an minus 1. And this is A of 1 over Z. Okay. The second step is we're going to calculate A1 of Z, which is going to be line 3. And to do that, we take the 2 by 2 determinants as below. So having an, a0, an minus 1, a1, a1, a0, an minus 1, an. I'm going to calculate the determinant using these entries. So we're gonna calculate CK, and CK is gonna equal to AN, A0, AN minus 1 minus K, and AK plus 1. So this one is going to be used for Z0. This is for Cn minus 1. This is for Cn minus 2, and so on and so forth. Okay. Now line 3 becomes Cn minus 1, Cn minus 2, all the way to C0. So the third step, we're going to reverse line 3 to get line 4. And we're going to repeat step 2. Okay, so we're going to continue with this. And we're going to be checking that all odd lines represent a subsequent iteration of A1 of Z. And we're going to test for the stability. That is, A of Z is sure if and only if the first entry of every odd line is larger than the last entry of every odd line. And therefore, the fifth step, we can stop when either if the short test fails, and in this case the system is not stable, or B, when line with only 2 entries, with line with 2 entries passes step 4. And in this case, the system is stable. How did we determine the stability of continuous time systems? Who studied control? Ralph Hurwitz. Excellent. Yes. In continuous time system, we've done something similar that we called, or the technique was called Ralph Hurwitz. Okay. So let's do an example and see what all this means. I mean, the test is much easier than the description of the test, which is a good thing. Okay. Excuse me. Okay. Okay. Let's do an example together, so nobody is bored. So let's say we have h of z that is equal to z squared plus 2z plus 1 divided by 12z cubed minus 4z squared minus 3z plus 1. How do we calculate the determinant A, B, C, D? What is the determinant equal of this matrix? AD minus BC. Is that what you said? Yeah. Okay. So we're going to determine whether this system is stable or not. So the first step, according to the steps that we laid down, we're going to start with line number 1. We're going to write the coefficients. We have the polynomial in descending order, so it's already ready. We're going to write the coefficient 12 minus 4 minus 3 and a 1. What is the next step? Reverse them. So we're going to have a 1, a negative 3, negative 4, and 12. We're going to write a line here. So this is line 1, line 2, line 3. Line 3, we're going to be calculating the coefficients from the two lines that are above it. What goes in here? The determinant, which is, so I'm going to write it here, is going to be a 12, 1, 1, 12. So I'm going to take this with this. 12 times 12, 144, minus 1 is going to be 143. So this entry is 143. What goes in here? I'm going to take the determinant of 12 and 1, negative 3 and negative 4. Negative 12 and 1. 12 and 1, negative 3 and negative 4. 12 multiplied by negative 4 plus a 3 is going to give me negative 45.
Would it be negative 52?
Mm,
No, wait, minus.
Negative 48 minus a 3, negative 45.
Forgot to double negative.
And then we're going to calculate the next entry, which is going to be a 12, a 1, and negative 4, and negative 3. And this is going to give me a negative 32. So I'm going to have minus 32 here. What do? We're going to check to make sure it's a short. Is the absolute value of 143 greater than negative 32?
Yeah.
Yes, so therefore we continue. So we're going to check here. Yes, therefore continue. What are we going to do? We're going to reverse this line. So we're going to get negative 32, negative 45, and 143. We're going to do something similar to how we calculated these entries. 143 times 143 minus negative 32 times negative 32. So 143, negative 32, negative 32, and 143. And that is going to give me 19,425. And then I'm going to calculate 143 times 45 times negative 45 minus negative 45 times 32, which is this entry here. 143, negative 45, and negative 32, negative 45. And that is going to give me negative 7, 8, 7, 8, 7, 5. We have only 2 entries in the row, so we can stop. We can check to make sure it's a sure. So we're going to test whether the absolute value of 19,425 is greater than the absolute value of 7,875. Yes. Therefore, the system, the polynomial, is a sure. And this means the system is stable.
We can stop because there's 2.
Yeah, because there's 2.
So, what is this doing? Like, I'm having a hard time, because before we have to get the poles, but by doing this trick with the determinants, is it like the equivalent of like a division, or what is it doing?
I mean, how it works is not intuitive.
Sure,
Right, but
I'm saying,
this-
like, what is the underlying, why does this work?
It works because if all the roots are within the unit circle, then all these entries are going to be the absolute value of them greater than these. Does that make sense?
No.
If all the poles of the polynomial are less than 1, then this polynomial, this coefficient is going to be greater, this coefficient is going to be greater than this coefficient. And all the iterations are going to have this coefficient greater than this coefficient. Does that make sense?
I just trust it. I have faith.
Yeah, I mean, try it. See if you can find a violation to the rule.
So, can you scroll back up to, so I can see like how the elements of the matrices are selected?
Mm-hmm. So,
Because I'm kind of.
so we have the 12, negative 4, negative 3, 1. Then we flip them.
Mhm,
Then this with this,
mhm.
this with this with this.
Okay, start
So this with this will give me this element. This with this will give me this element. This with this will give me this element. I mean, that's why I wrote these, the matrices, so you can calculate them. So you can see where they're coming from. Together? Now what you can do, or what you can try to do, is you can try to take some simple polynomials, z minus a multiplied by z minus b, and multiply them, and assume a and b are less than 1. And look at the pattern that you will get when you multiply these polynomials. Does that make sense? So, I mean, you can see it here. If both of these are z minus a plus b multiplied by z plus a multiplied by b. This is for only 2 roots. If a and b are less than 1, what is this a multiplied by b? Going to be less than 1, which is going to be less than the coefficient here. If this is greater than 1, it means there is a root that is violating this polynomial. See? And you can extend it like with a third row, with a third root and fourth root, etc. Okay. So you can add to it z minus c, multiply it, and you can verify indeed that is the case. Okay, let's do another example where it violates the Shor's polynomial. So h of z equals z squared plus 2z plus 1 divided by 6z cubed plus 11z squared minus a 3z minus 2.
to be, like, whenever we're doing the Z transform, do they have to be, does the denominator have to be equal to or greater than the order, like that denominator's Z of 30?
I mean, that doesn't matter.
It doesn't matter.
The order does not matter because we're only operating on the roots of the denominator. Does that make sense? However, what we have to make sure is there's no poles that will cancel with the zero
That's
here.
okay. Yeah.
So the assumption is there's no cancellation. Otherwise, you could have a pole here that could have cancelled with a zero. Okay. Okay, so doing something similar, the Jerry's test, 6, 11, -3, -2, -2, -3, 11, and a 6. We're going to calculate 6 times 6 minus 4. It's going to be 32. Oh, first we check that indeed 6 is greater than -2, so we can continue. This is the first line. So we continue the next entry. 6 times 11 minus 6 is going to give me a 60. 6 minus 6 times -3, -18 plus 22 is going to give me a 4. We check again. 32 is greater than 4. We continue. All good? 6 times 6, 36, minus 4, 32. 6 times 11, 66, minus 6, 60. 6 times -3, minus 18, and this is going to become plus 22. It's going to give me a 4. Okay, so we reverse this row. And we continue. If we multiply, 32 times 32 minus 16 is going to give me 1,008. If we multiply 3260 minus 60 times 4 is going to be 1680. And if I check if it is sure, 1008 is less than 1680. And therefore it failed. Therefore, the system is unstable. Together? Okay. Any questions? Now, when we do in control with the Rauch-Hurwitz, and probably those who took control, we've done the polynomial with the roots. Anybody remembers when we have 2 roots, 3 roots, and then we multiply them, and then we looked at the structure of the polynomial, and we saw the pattern of what the location of the roots, how it will translate into the coefficients of the polynomial. Next, I mean, the coefficients of the polynomial are determined by the location of the poles. Make sense? So this coefficient of z represents the summation of the poles. This is the multiplication of the poles. So there's a pattern, and this technique will help us determine whether the poles, if any of the poles has a value that is greater than 1. Questions? Okay. Since Renee is leaving, this brings us to the next topic that we're going to be covering, which is the digital filter design. And we're going to be spending quite a bit of time on this topic. Digital filter design. So now that we have a very good understanding of the discrete time systems, we are ready. I mean, we've done analysis of the system. We are ready to start designing filters. So let's look what we have here. So most of the signals that we're going to encounter in real life are going to be analog signals. However, what we like to do is we like to be able to process them using a computer. So therefore, if I look at what we're trying to do, the size does not indicate anything though. Just to emphasize, this is the new topic that we're covering. So we have a continuous time signal, xc of t, and we're going to be able to process it using a computer. So in order to do that, what do we have to do? Convert it to digital. So we're going to multiply it by a sequence or impulse train, and we're going to convert to a sequence of digital values. So this is our analog to digital convergence. At the output, we're going to have a discrete time signal, x of n. So this x of n is now inside my computer. I can operate, or inside my microcontroller or my microprocessor, and I can operate on it. So therefore, I'm going to be able to take this x of n and operate on it using this discrete time system. And after I operate on this signal, x of n, this is going to give me an output that I'm going to call y of n. Together? Then I'm going to take this y of n, I'm going to convert the sequence to impulses or impulse trains. And then I'm going to pass it through a low pass filter. And this is going to give me a continuous time, y continuous of t. Which one? Yeah, low pass filter, because I have impulses. This is how we do the digital to analog conversion. Remember? So this is going to look something like this. Impulses. Then the low pass filter is going to look like the things that we've seen. And overall, the output is going to be the continuous time signal back. Is that clear? Makes sense? So this is just a representation of what's happening. We have a sequence. These are numbers. How do I convert it to a continuous time signal? I generate impulse train, then I filter it, and that will give me a continuous time signal that I'm going to call y continuous. Okay. So overall, what we're trying to do is that if I look at this system, I have a continuous time signal xc of t, and I have an output yc of t. So I could have done the same thing. Instead of taking this signal, converting it to a digital signal, and then using a discrete time filter and converting it back to a continuous system, I could have designed just an analog filter that will just take the xc and generate y of c. So what we're trying to do is to design our discrete time system so that the equivalent of all this is the analog filter that I have here. Does that make sense? Okay. So our goal is to design a difference equation to perform a specific filtering task. Okay. So what are the tasks that the filter does? What do we use a filter for?
To attenuate some signal and let through another?
To attenuate some signal and not attenuate other signal. So what does that does? What does that do? Separate a certain band. Does that make sense? So we can have specific frequencies or band of frequencies at the output. What else? Smooth the data. Yes, we can use the filter to smooth data. What else? If I have a signal and I know the content of my signal is only within a certain band, then I don't want all the rest of the bands to be in my signal. So I can remove, for instance, noise that might be outside the band of interest. We can compensate for non-ideal channel. So if I look, for instance, in communication, when we tune our radio, what do? So I have all kind of channels that are playing or that are broadcasting on the air. So this is the frequency. And when I select a specific channel, what am I doing? I'm just allowing that channel to pass through, and I'm filtering all the other channels out. So if I'm listening to this station, for instance, I want a filter that might look something like this. It's going to remove all the other channels and only allow the channel that I'm interested in to go through. The same thing if we are communicating and you are talking on this channel, I'm talking on this channel. When I get my reception, I just want the channel that belongs to me to go through, and I want to filter all the other channels. Okay. So therefore, the effective performance of our digital filter that we're going to be designing is going to be such that if I were to replace all the system that we had above, is going to replace this, is going to have an H effective of W. This is X of T, and this is YC of T. So the digital filter in the system that we talked about above is going to be equivalent to having a filter H effective of W. So if I have this filter, if I have the H effective filter that I'm trying to design, so given this desired H effective of W, how do you design H of Z? Is that clear? Trying to do. So you give me a signal, an input, you give me an output. Therefore, this filter is needed to go from this input to the output. I want to be able to find H of Z such that when I plug in H of Z in the block diagram that I had above, H of Z is going to act as if it was an H effective that I have here. Together? And this is what we're going to be investigating when we're discussing the filters. So let's look at the design steps that we're going to be following. So the first step in the design of the filter is to determine the specifications of the desired effective filter. And let's look at a typical filter response and see what parameters that will determine the performance of this filter. Now also, I want to mention that we're going to be designing a low-pass filter, and then later on we're going to learn how to take this low-pass filter and convert it into any other filter. Does that make sense? So all what we're going to see is a low-pass filter, but somebody's going to say, okay, what if I want to design a band-pass filter or band-stop filter? We'll look at how we convert it from one filter to the other. But everybody familiar with low-pass filter, high-pass filter, band-pass filter, band-stop filter? Yes? Okay. Okay, so if we have a filter, this is how we're going to determine the specifications of this filter. Okay, the scale does not matter. So a filter response might look something like this. This is my omega, and this is my H effective of W. In general, we might have ripples in this band, we might have ripples in this band. What do we call this band? Pass band. Excellent. So this band here we call it the pass band. What do we call this band here, stop band. Yes. So this is our stop band. And what do we call this between the pass band and the stop band?
Quality factor?
No, the transition region. Is the label clear? Between here, between this and this is the transition region because we transition from pass band to stop band. Okay. Now we're going to assume the maximum response is equal to a 1. And then this value here is equal to 1 over 1 plus epsilon squared and all underneath the root. So this value here is equal to 1 over 1 plus epsilon underneath the root. Make sense?
Is epsilon the distance between the two blue lines?
It will determine this, yes. It's not the distance, but it will determine that distance. I mean, if epsilon is 0, then there is no ripples. I'm going to be just a straight line. The larger the epsilon, the more I'm going to dip in.
And what is the x of the epsilon, I'm sorry?
Squared.
So the whole
1 over 1 plus epsilon squared and the root of all that. Okay. We're going to define this distance as the passband repo. And we're going to refer to it as R. And we're going to define, or this point here is going to equal to 1 over A, where A is a measure of the acceptable attenuation. So this is 1 over 1 plus epsilon squared underneath the root. And this point here is 1 over A. Now we're going to also define this frequency here, and this frequency is we're going to call it omega cutoff. And this frequency here, we're going to call it omega stop. Since this is the stop band, this is omega stop, this is the cutoff for the pass band. Is that clear? Graph? Okay. So this is going to be our reference for all the filters that we're going to be designing. R is the maximum acceptable passband ripples. And we're going to define this in dB. And therefore, this is going to equal to, R is going to equal to 20 log 1 plus epsilon squared to the root. And therefore, this is going to equal to a 10 log 10 of 1 plus epsilon squared. So R is defined in dB. And it's going to equal the 20 log of 1 plus epsilon squared square root. And therefore, we can convert from R in dB and calculate epsilon by taking 10 to the power of R over 10 minus 1 square root. which is from this equation, r over 10, 10 to the power minus the 1, square root of all that. A, as we said, is a measure of minimum acceptable attenuation. And omega stop divided by omega cutoff is the transition ratio. Together? Now just looking at this graph here, if this was a filter, what do you like about this filter? What do you like about this filter? What do you not like about this filter?
Don't like the ripple.
We do not like this ripples here. We do not like this ripples here. What else we do not like?
The transition size,
Which one?
the transition region size.
Oh, the transition. Excellent. Yes, we do not like the transition here. Makes sense? So we want this ripple to be as small as possible. We want this to be also as smooth as possible. But nevertheless, as we will see, there is, when you're designing a filter, there is expense for any specifications that you need to meet. So the more ripples you can tolerate here, it means the filter order is going to be smaller. The less ripples you want, the higher the filter order. The smaller the transition region, the higher the filter order. The bigger the transition region, the higher the filter order, and so on and so forth. Make sense? So it's all a compromise that will determine eventually the cost of your filter. Okay. So the design steps, we're going to look at the specifications of the desired filter. The second step, we're going to select the sampling frequency. Or the sampling period, and we're going to map the specifications to the discrete time frequency. And if you remember, omega, the discrete time frequency, is equal to W multiplied by T. And omega between negative pi and a pi. So we started, this is the filter that I want my digital filter to emulate, to act like this filter. So we have these specifications. I'm going to take all these frequencies. I'm going to convert them to a discrete time frequencies. So now I have all the amplitudes here, and I have the omegas. I converted omega c, omega stop to our discrete time frequency omega. Finally, the third step is to determine filter implementation. What are the choices that we have? We can have two types of filters. We can have an IIR filter, where H of Z is equal to B of Z divided by A of Z. Or we can have an FIR filter, where H of Z is just equal to B of Z. There is no A of Z. Why does the FIR filter not have A of Z?
It's real time.
No. What else? Why does the FIR filter look like this and the IR filter look like this?
It's only on the input.
Yes, and that means, remember, h of z is y of z over x of z. So, I mean, we know how to go from h of z to a difference equation. So if h of z is y of z over x of z. So if my filter y of n only depends on the input, then I should have h of z, just have a numerator. Does that make sense? So I'm going to have something that looks like this. Z squared plus z plus 1. Multiply across, I'm going to have y of n that is equal to y of n plus 2, y of n plus 1, y of n. If my filter, if I have a numerator and denominator, what is that going to give me? Y of z over x of z. When I calculate y of z, when I multiply across, y of z, when I convert it to the time, is going to have multiple terms that multiply y of n. When I move it to the other side, I'm going to have y of n that depends on the output and on the input. Is that clear, everybody? Sees that? So when the output is only a function of the input, it means I don't have a denominator. When the output is a function of input and output, then I'm going to have a denominator. Okay. Now, before we start designing filters, we're going to emphasize that when we design a filter, the filter will only work on the frequency that is at the sampling frequency that is it designed for. So let's look at an example. So let's say we have a communication system. And we have a receiver that needs to pick up a signal. And if I look at the frequency, if I look at the frequency band, it looks something like this. Up to 100 hertz, I have this signal. Then I have another signal from 100 to 200. Then I have a third signal from 200 to 300. And this is negative 300. We're going to call this channel 1, channel 2, and channel 3. So this is channel 1, this is channel 2, and this is channel 3. And what we want to do is I want to be able to remove channel 1 and channel 3. So I want to design a filter. I'm going to use digital filter design. We're going to remove channel 1 and channel 3. And therefore, I'm going to design a filter. What is the effective filter going to look like? A bandpass filter. Very good. So this filter that I want to design is going to operate from 100 hertz to 200 hertz. This is the frequency in hertz. And I want a filter that looks something like this. And I'm going to call this my H effective of W. Or actually, let's keep this as a W and a W. So if I have a filter that looks like this is a bandpass filter. It's going to remove everything above 200, everything below 100. And in the next class, we'll see how this works and the impact of the sampling frequency on this filter. Any questions? Okay, I'll stop here.